Okay, anybody have any questions about anything, practice problems or stuff I've been talking about in class before I start? I wanted to do one example just to sort of demonstrate like how to go about the first few problems in the 1D kinematics practice problems. So let's say that this hiker, he has very weird walking form. He's tiny too. Why is he so small? He'd be so much easier to draw if he were bigger. He's sensitive about his left leg too. So he starts out here at this point A. He goes to the point B. Then he realizes he forgot his keys, goes back to A, and then goes to C. Okay. And let's say that these distances are a quarter mile, and this distance is 0.15 miles. Okay. Okay, so this motion happens, you know, whether you're there to take data or not, right? I mean, whether you're there to observe this guy's going about his business. So before we can put numbers to this, we have to choose three things. We have to choose a zero position, a positive direction, and a time, an instant to turn on the stopwatch, a zero time. When we do those things, it doesn't change anything about his motion. He doesn't even have to know we're there, you know. So his motion is still going to go from A to B to C, but the values that we associate with it are going to change based on what choices we make. So I'm going to do one. This is sort of different from the example problems, but I'm going to choose my zero position to be at B. So let's say zero position at B. Let's say the positive direction is to the left. And we'll choose the time equals 0 instant to be when he starts walking. And what I want to do is draw a position versus time graph. So the way to approach all these problems, the first thing is draw out the motion, really just like I already did here. Because this is the thing that doesn't depend on your choices. The motion is going to be the same no matter what. Now, once we make these choices, we can associate values with these. And I guess I have to give times for all these. Let's say, so this would be given as part of the problem, but let's say the first leg he walks a quarter mile in 4 minutes. Then after he realizes he lost his keys, he walks the next leg in 5 minutes because he's demoralized. Then by the third leg, he's exhausted, so it takes 6 minutes. And then that fourth leg from B to C, that's a little shorter, so let's say that takes 3 minutes. Okay, that would be given as part of the problem. Okay, so now what you should do is once you choose the zero position and the positive direction, you can associate position values with all these points, okay? So if the 0 position is at B, then the value at B is 0, right? I mean, that's the definition you made. The positive direction is towards A from B. We know that it's a quarter mile. So if A is a quarter mile in the positive direction, what position value is going to be associated with A? Yeah, 0.25 positive. So 0.25 meters is the position value at A. And what's the position value of C going to be? Right, that's in the negative direction, a distance of 0.15. So this value is going to be negative 0.15 meters. Miles, I'm sorry, it should have been, yeah. That would be a very short walk. So now to graph it, there's position. Time is this way. And we know there are going to be times that, you know, this time just keeps adding up. So there's going to be 4 minutes, 9 minutes, 15 minutes, 18 minutes total. So there's 18 minutes. 15 minutes. 9 minutes is right here. 4 and 5. Okay. So if he starts at A, what's his position when time is equal to 0? We know he starts at A. That doesn't change based on the values we choose. The numerical name of A now is positive 0.25 miles. And so when time is equal to 0, he's at 0.25 positive. The other point is this. So he starts out here, right? At the end of that first leg, so at the end of 4 minutes, he's at the point B. What's the numerical value associated with B? 0, yep. So the next thing is here, so we can draw this line. At the end of the second leg, he's back at A, so what's the numerical value of that? Yeah, back to 0.25. At the end of the third leg, he's 1, 2, 3. I guess I'm making another break here. So at the end of the third leg, he's back at B. So what's the value there? 0 again. I didn't draw that very well. This one should be longer than this one. But and then finally, the fourth leg goes from B to C. So at the end of the fourth leg, what's the numerical value? Right. And so it ends up here. And so that's what a graph of position versus time would look like. And there's like 1 or 2 questions with a bunch of subparts on the 1D kinematics practice problems where you just have to do that. And maybe you can imagine, having gone through this process, like what we choose as the 0 position and what we choose as the positive direction has an effect on what this graph looks like. What we choose as the positive direction has the effect of flipping this upside down or leaving it in the same orientation. And what we choose as the 0 position has the effect of making this graph translate up and down vertically. Does anyone have any questions about that? So you can almost exactly apply this approach to those questions. Okay. Then let's do another 1D kinematics practice problem, or another problem, example problem. So let's say that you have this, oh boy, that doesn't look good for this guy. So this is one of those circus cannons where they fire the human cannonball. I don't know why they made this particular model with such a narrow opening. That's going to really hurt as he goes by. But he's just crouched down here getting ready to go. And here's a spring and a platform. So, you know, even though like they have like the monkey come up and light the wick and all this stuff, there's actually no explosion going on. I know you thought that he probably was, they used gunpowder for this, but no, there's like a platform and a spring. But so when this is released, he's going to go from here up to the nozzle, and we're going to assume that it's constant acceleration the whole time he's going. So this distance that he travels until he gets to the gun muzzle is 3 meters. And over these 3 meters, he goes from rest to a speed of 12 meters per second. And so I have 2 questions about this. What's the acceleration during that interval? And second, how long does this path take? How long does it take him to cover those 3 meters? Okay, this is a constant acceleration problem, so we're going to do it by going through those steps for constant acceleration problems. We're going to use those 3 equations. So the first step is to choose 4 values, the 3 that I just talked about choosing for that other kind of problem. So we have to choose when time is equal to 0, we have to choose position equals 0, and we have to choose a positive direction. And then we have to choose a 4th one to use these equations, and that's an instant corresponding to time final. The first 2 are arbitrary, the position ones. We can do the problem no matter what we choose for these, but some choices make the math easier than other choices. So for position equals 0, what seems like a sensible choice for position equals 0? Yeah, let's choose position equals 0 when he's down here at the start of the acceleration. So I'll say his location at the start of the acceleration. And then what about a positive direction? It's a one-dimensional motion, so we either have to choose the direction of motion or the opposite of the direction of motion. I tend to usually choose the direction of motion, but you could do it the other way. So the positive direction is the direction of motion. And now we have to choose those 2 time values. These are not arbitrary. These we have to choose based on where we have information and where we're trying to get information. So time equals 0. The only rule is time equals 0 has to be before time final because we want a positive time final. So where do we know things and where do we want to know things? At what instance? Yeah, right. It's not necessarily the stop, but yeah, the end of that motion. Yeah. We know stuff at the start of his acceleration. We know his position based on where we chose our position equals 0. And we also know his velocity. So this is going to be at the start of the acceleration. And time final, that's going to be at the end of the acceleration. I'll say when he reaches the 3 minutes, 3 meters. Okay, and now we have to start to write down a list of which variables we know and which variables we want to find. So I'm just going to go through the possible variables one by one. Do we know the initial position? That's the position when time is equal to 0. And we happen to know that just because we chose our 0 position to be his location when time is equal to 0. So pi is equal to 0. Do you know p final? We know he's traveled 3 meters. Is it going to be positive 3 meters or negative? Right, positive because we chose the direction that he's moving to be positive. Do we know the initial velocity? It's 0 because he's at rest. Do we know the final velocity? Yeah, that's given. So 12 meters per second. Is it positive or negative? Positive because he's moving in the positive direction. Okay. And do we know acceleration? No, that's what we want. And do we know time final? No. For part B, that's what we're trying to find. For now, though, part A, we don't care about that. So I'll just leave that off. Okay, do any of those 3 equations have A in it and everything else in it appears in this list? Yeah. Right. Well, want is just the stuff that we're asked for. You know, I mean, if we're asked for something, we want it. If we're not asked for it and we can solve the problem, get what we're asked for without the other thing, then we're happy doing that too. To answer B, yeah. I was just, so yeah, you could put it like sort of on deck here. For now, though, we're just doing it one at a time. I guess my thinking about it is we're looking for a single equation that's going to get us what we want. That's what we're hoping for. And in a single equation, you can only solve for one variable. So I tend to only put one variable here in what we're looking for. Okay, so equation 6 will solve this. That's the one that says 2a times the quantity position final minus position initial is equal to vf squared minus v initial squared. So 2a is equal to 3 meters minus 0. 2a times the quantity, 3 meters minus 0, is equal to v final, that's 12 meters per second squared, minus 0 squared. And if you multiply all this out, you get 6 meters times the acceleration is equal to 144 meters squared over seconds squared. And to solve for the acceleration, you want to divide both sides by 6 meters. So acceleration is equal to 144. I'm going to write it as meters times meters over seconds times seconds. And to divide by 6 meters, you multiply by the reciprocal. So 6 meters goes down here. 1 meter cancels with that meter. And you get a value of 24. So 24, and the units you're left with are meters per second squared. Any questions about the calculations? Okay. There are 2 things you can look at here to make sure that it makes sense. First, the units. These are the units that we got mathematically. Are those the units we'd like for acceleration? Yeah, acceleration has to be length per time squared, so that part checks out. That's good. And then the second thing is, does it make sense that we got a positive acceleration? Yeah, it makes sense in the sense that he's moving in the positive direction. So velocity is positive, and we know he's speeding up. So acceleration, if he's speeding up, acceleration has to have the same sign that velocity does. So we'd expect it to be positive, and it is. Okay. So those 2 sort of sanity checks make us, more confident about our answer. Can a human being survive that acceleration? Anyone have a opinion about that? Well, that's about 1 g of acceleration is 9.81 meters per second squared. So this is about, 2.5 Gs. So yeah, you can survive that for, actually, you could probably survive that for a pretty long time. So that's good. I mean, that, like if you're planning a circus, like that's one thing you want to check out before you invite the people. Okay, so now for part B, we want to figure out how long that takes. Is there any reason to change any of those specified values? So the only reason that you would have to change those, sometimes the math can be a little easier if you change the position equals 0 location or the positive direction. But the only reason you'd ever have to change anything is if you're looking for, you're trying to solve for something that's happening at a new instant. Okay. In this case, we're looking for time final. So we're looking for something at the end of our interval, right, that we chose before. So those 2 times that we specified will work fine in this case. Okay. So no reason to change. No reason to change the specified values. And so what that means is we still know all the things we knew for part A. And now we also know the acceleration. We learned one more thing. Okay, so if we list everything out, the list of variables we know PI is equal to 0, PF is equal to positive 3 meters, VI is equal to 0, VF is equal to 12 meters per second. And now we know that acceleration is equal to 24 meters per second squared. And what we're trying to find is time final. So of those three equations, which one has time final in it and everything else in it appears here? 4 works. I think 5 works too, right? So 2 equations work. V final is equal to V initial plus A T final. And also P final is equal to P initial plus V initial TF plus 1/2 A TF squared. If you have your choice between these two, I guess the first one is simpler. So you might as well use that one. But let's do it 2 different times and just see that we get the same thing. Because there's one thing about using the second one of these 2 equations that you have to be aware of. Okay, so using this first equation, 12 meters per second is equal to 0 plus 24 meters per second squared times TF. And so divide both sides by 24 meters per second squared. And you get, so 12 meters per second. To divide by 24 meters per second squared, it's like multiplying by 1 over 24 meters. The meters go in the denominator. Now the seconds, we're talking about the reciprocal of this, so the seconds go in the numerator. Does that make sense? This is equal to T final. So the meters cancel, 1 second cancels, and you get positive 0.5 seconds. So do the units make sense? We want a time and we got seconds, so that's good. And does the sign make sense? Does it make sense we got a positive time? Yeah, we only want to deal with positive time. So if you ever do a calculation and you get a negative time, it means something went wrong. Okay. But let's do the same thing with the second equation here and see that we get the same answer. Okay, so what's position final? Yeah, 3 meters. So 3 meters is equal to, what's position initial? 0 plus 0 times time final plus 1/2 times the acceleration, 24 meters per second squared, times time final squared. So we can simplify this and we get 3 meters is equal to 12 meters per second squared times time final squared. And now to get time final squared by itself, I want to divide both sides by 12 meters per second squared. So 3 meters divided by 12 meters per second times second is equal to time final squared. The meters cancel, and we're left with 0.25 seconds squared. Any questions about that step? Okay. So now to get time, we don't want time final squared, we want time final. So we're going to take the square root of both sides, and we get that time final is equal to, what's the square root of 0.25? 0.5. Square root of seconds squared is seconds. And then there's one more key thing that we need here. Plus minus, yep. So this equation above would be true whether time final was negative 0.5 seconds or positive 0.5 seconds. So we have two possibilities. This is always going to happen whenever you take a square root or use the quadratic formula to find a variable. And then you need to come up with some reason to choose one or the other one. You can't just, choose one at random. Each one always means something physical, and we have to choose which one makes sense to us. If you're dealing with time, it's sort of easy. We never want to deal with negative times, so this is the one we want. Okay. We'll do other examples where it's not as automatic. You have to sort of think physically about what's happening in the problem. But so we get time final is equal to positive 1/2 second, the same thing we got with the other equation. Any questions about that approach? Okay. So the next big topic in constant acceleration kinematics is free fall or projectile motion. And you think, like in everyday speech, you think of these two. Well, I don't know if you use either of these in everyday speech, but I think people tend to think of free fall as being a motion straight down and projectile motion as being a motion that's out or up or something. But I'm going to use these two interchangeably. And what they mean is this. So these two terms are interchangeable. And they mean that the only force, or I should say, the only significant force acting on an object is gravity. So when is this technically true on Earth, that the only force acting on something is gravity? It's never true because there's always air resistance. And so it's always an approximation. In a lot of cases, it's a really good approximation. And so we need to talk about like when you should feel okay making this approximation and when you shouldn't. So when is it reasonable to make the free fall approximation? Well, the first criterion is nothing can be touching the object except air. So nothing can be touching the boundary of the object. The second one is like a little more, a little trickier to define, and that is the force of air resistance has to be much smaller than the force of gravity. Um, so, okay. How do you write okay like that? Okay. um, so when's that? You know, I'm just like, I didn't answer the question. So when is air resistance negligible compared to the force of gravity? Okay, so that's the next thing to talk about. What affects air resistance? And there are three things that affect air resistance. Well, you know, that's a bad way to write this. Sorry, just erase what you have there with your little electronic pen. So what affects air resistance's influence on motion? And there are three things. The first one is the mass of the object. The more massive an object is, the less influence air resistance has on its motion. So I guess let me write it like this. If you increase the mass, it leads to a decrease in air resistance in air resistance's influence. The second one is the surface area, and to some extent the shape also of an object. So I'm just going to say surface area, but the shape can have an effect too. But for the most part, the more surface area you have, well, let me do it this way. If you reduce surface area, it leads to a reduction in air resistance. Okay, so the mass and the surface area thing, think of examples where you're only changing one of those two variables, and intuitively I think you sort of know what would happen. Like say you took a beach ball, okay, filled with air, and you took another beach ball and somehow filled it with steel, you know, like one would be really light, one would be 1,000 pounds or something, and you drop them both from the top of a building. You know intuitively that the steel one would hit the ground first, right? That's because it's so much more massive. Even though they have the same surface area, air resistance is going to have less influence on the motion of the one that weighs 1,000 pounds than on the beach ball, right? And so air resistance would hold the regular beach ball, like keep it from accelerating as much. And then imagine this now. Imagine you take the beach ball that's full of air. I don't know how much it weighs, but say it weighs like 100 grams or 50 grams or something. Like it has some weight. And then take a piece of steel that has that same weight. Like now it's going to be a lot smaller, right? So say you'd have a piece of steel the size of a marble and you'd have a beach ball, and you drop both of those from the top of a building. you know that, again, the steel piece is going to hit the ground first, because even though they have the same mass, the beach ball has a lot more surface area. And so there's going to be a lot more air resistance on the beach ball than there is on the little marble made out of metal. And then the last thing that affects air resistance is the speed. The slower something's moving, so if you decrease the speed, it reduces the amount of air resistance. And my example for this, I just like bike racing, so I guess that's probably why I don't race, but I like watching it. And like if you ever watch the Tour de France or anything, bike racing is a really complicated thing. And it's complicated all because of air resistance. You know, like in bike racing, even the best person, even if he's the best by far, he couldn't just ride off and beat everybody, because they can work against air resistance together as a group to catch up. Okay, so the only time that a bike racer really has to deal with air resistance on their own, there are two types of races, like in the Tour de France, two types of stages. One is the time trials, where they send them out one by one, and they just have to ride the entire thing by themselves. And the other is the stages where they're riding up in the mountains. And in the mountains, people get spread out. They're not able to stay together. And so those are the two times that bike racers, like, you see them actually dealing with air resistance on their own. And so you would expect, based on that, like maybe they wear different outfits for all the different stages, and they ride different bikes. You would expect maybe in the time trials and the mountain stages, they would wear the same outfits, ride the same bikes, because in both cases, they're having to deal with the air resistance on their own, you know? But that's not the case. In the time trials, let's see. They wear these skin-tight suits made out of like rubber material. They wear these crazy helmets with the teardrop backs. I should have practiced this. Okay, something like, they don't do that. That's actually a scooter. But anyways, in the time trials, they look like this, essentially. And then in the mountain stages, instead of wearing the rubber suits and everything, bending all the way over, all the way so they're parallel with the ground, wearing the funny helmets, they just wear regular cycling clothes. They don't even put their hands down in the drops, the lower part of the handlebars. Like they spend half their time just up looking like they're biking to get groceries, you know. Their biking jerseys are all unzipped and open. They're wearing regular helmets. This is a terrible illustration of this. It's harder to draw because I'm drawing it sideways. Okay, so what's the deal? Like, why are they wearing and riding, say, $15,000 worth of stuff designed to fight through air resistance, avoid air resistance in the time trial, and here they're just wearing regular stuff? They don't seem to care about air resistance at all. That was a long story, but the answer is they're going really fast in the time trials, and relatively they're going really slowly in the mountains. In the time trials, they're going, over 30 miles an hour. In the mountains, they're going around, 10 to 15 miles an hour. And that distance in the speed, that difference in the speed is enough that the only thing that matters in a time trial is getting through air resistance, and it's almost not even worth thinking about in the mountains. So speed makes a big difference too. Okay, so I want to just give a few examples of things, cases where the free fall approximation would be a good one and cases where it would be a bad one. So the first case I can think of that would be where the free fall approximation would be a really good one is the shot put, like people watch track like once every 4 years during the Olympics because they're too lazy to turn off the channel when, rhythmic gymnastics is over or whatever. And anyways, shot put is like the huge guys, 300-pound guys with the little steel ball. They spin around and throw the ball as far as they can. And the thing weighs 16 pounds, so you can't throw it that far, So that event's called the shot put. The ball weighs 16 pounds, and it's pretty compact. It's only this big, So sort of relatively thinking, compared to other balls, other sports and whatever, this thing has a lot of mass, not much surface area. And it also isn't going very fast because it's so hard to, so heavy. They're only throwing it probably 20 to 30 miles an hour. It's not like a baseball going over 100 miles an hour or whatever. So if you're trying to do a calculation of the motion of the shot in this event, you would never, almost no matter what accuracy you're looking at, you would never worry about air resistance. It just doesn't matter. Another good approximation would be a baseball that you just dropped from like shoulder level. Okay. It's not as massive as the shot, but it has a pretty small surface area. It's not super light, and it's not going very fast in the time it takes to get from your shoulder down to the ground. Okay. So if you're trying to do calculations about that motion, the free fall approximation would be good. A bad approximation, think of like a feather or a sheet of paper. So both of those, when you let go of them, they flutter down to the ground like this. That fluttering is entirely air resistance. And the reason that there's so much air resistance, that air resistance totally dominates its motion, is they don't have much mass, they have a ton of surface area, and, well, the speed doesn't even come into it. Even though they're moving slowly, that high surface area and low mass is enough to make up for how slow it's going. And then the other example that I want you to keep in mind is a baseball that's been hit off of a bat. A baseball that's been hit hard by like a professional baseball player. I don't know how fast it's going, but I assume it's a little over 100 miles an hour. That's fast enough that air resistance has a huge effect on the motion. So I want you to notice that baseballs are in both of these two columns. And keep in mind that it's not like the object itself that determines whether free fall is a good approximation. It's the object in whatever situation you're thinking of, it's hard to come up with examples where uh, a feather, say, is moving so slowly that the free fall approximation would be a good one, but that is actually the case. If it's going slowly enough, you could make a free fall approximation with a feather. On the other hand, like a shot, this 16-pound steel ball, if it was going the speed of sound, air resistance would you would not want to be around. You'd want to be far away, and air resistance would have a big effect on its motion. You know, it just would have to be going really fast for that to happen. Okay. Any questions about that? I want to show an example, a YouTube video. This is kind of cool because, so this free fall approximation, sometimes you hear people make fun of physics class because it's like, oh, well, in a vacuum, this would happen. And, you know, but there aren't any vacuums. So how do we know, first of all, like, are we just making it up? Well, actually, you know, you can evacuate chambers. You can't get an exact vacuum, but you can see that the things that we're talking about are closer to holding true the less atmosphere you have. And when they did the moon landing in 1969, on the moon, there's no atmosphere at all. So actually, all these things that theoretically happen on Earth, if you're in a vacuum, you can actually test them on the moon. And so there's a video of this guy in his spacesuit holding a feather and a hammer and letting them go at the same time. And, you know, I'll be damned if the feather doesn't just drop just like the hammer, you know? It's funny. So we're going to watch that now. And you're going to pretend you think it's funny. Okay. Oh, you can't hear anything. Wait. Oh no, he's gonna do it. Let's. ridiculous. Okay, I'm going to narrate it. Okay. That's okay. I'll just tell you when to look. Okay, so it's pretty grainy, but he has a feather in his left hand and he has a hammer in his right hand. There's the hammer. Oops. The left hand list. Did you see that? Isn't that weird? All right, worth all the time. Apparently, I don't remember how I noticed this, but I think I heard something like just in passing, some conspiracy movement, and so I think I just went to some website for a few minutes, and on the like one of the things that's on there as like proof that the moon landing didn't ever happen is that apparently from the video they say like you can tell from the video something about the way it sparkles or something, that feather is actually made out of metal, you know, like they actually made this metal feather. So I don't know, you decide. I'm not trying to push my beliefs, but all right. So we've been talking about when to be confident, not confident that something's in free fall. One thing you know for sure is if something is touching an object, it's not in free fall. As soon as it's touching another object, you can't assume free fall. Okay. But if all these conditions are met and you feel comfortable assuming that an object is in free fall, you know, even though there's going to be some error, you're comfortable that that error is going to be small. Here's what you know. So if you can use the Freefall approximation, then the acceleration is equal to 9.81 meters per second squared down. I recommend that you, you know, I've been saying how when you're doing constant acceleration problems, you get to choose what your positive direction is. But I recommend with free fall problems, just always choose your positive direction up. And if you do that, then the acceleration is always negative 9.81 meters per second squared. That's just, people tend to do it that way. There's no mathematical reason you have to have the positive direction up, but that's how people tend to do it. This is on Earth. So on the moon, actually, because the moon has so much less mass, the acceleration is considerably less than this. I think it's like a sixth or something. And you could see them bouncing around. Like it doesn't look like It doesn't look like moving on Earth. Okay, so what we saw in that video and what you need to remember is any things that you're treating like they're in free fall, any two things that you feel comfortable saying are in free fall, their motion while they're in free fall is just the same. If you drop a, say you drop a bowling ball and a 50,000 pound safe off of a building or something, like both of those, you feel comfortable with the free fall assumption. They're going to accelerate the same, and so they're going to hit the ground at the same time. Okay. The only times that that wouldn't happen is if you drop something that is closer to free fall than something else. Like if you dropped the bowling ball and then you dropped a ping pong ball. Okay. The ping pong ball wouldn't hit as fast as the bowling ball because air resistance is a bigger deal for a ping pong ball at that speed. Okay. And actually, there are fluctuations in the acceleration due to gravity based on how far you are from the center of the Earth, and I think also based on the location of the moon too. But it's not very much. Like at sea level, the acceleration due to gravity is like negative 9.8065. And on the top of Mount Everest, it's like negative 9.804 or something. You know, it's a very small difference. Okay. Any questions about anything on free fall? So let's just do a couple problems. Other than knowing the acceleration, really these free fall problems are just like the other constant acceleration problems. Oh, I did want to give a couple of common strategies. These are things that are going to come up in free fall problems pretty often. So common strategies for free fall problems. The first one, this is an important one to remember, is if an object is launched up into the air, you know that it's going to go up, slow down, eventually it'll reach a highest point and then come back down. At the instant it reaches the highest point, its velocity is 0. And we'll do some example problems where we use that fact. And then second, if you choose your position equals 0 to be at the ground, then position has to be equal to 0 when the object hits the ground. So like, for example, if you're trying to figure out how long it takes for an object, an object's launched up into the air and you're trying to figure out how long it'll take for it to land back on the ground. If you put your position equals 0 on the ground, then one of the things you can specify, one of your knowns, is that at your T final, when the thing hits the ground, where you're looking for information, your position is going to be equal to 0. Okay. Going along with this, what you should not assume, and this is an easy mistake to make, don't assume that the velocity is equal to 0 when the object hits the ground. That is a mistake that people make often, and it makes sense. I mean, if you think an object goes into the air, comes down, at the instant it hits the ground stops it. So just for an instant, it has 0 velocity. And that actually is true, you know. It does have 0 velocity for an instant after it hits the ground. The problem is, as soon as it touches the ground, it's not in free fall anymore. So our calculations can't get to that point when its velocity is equal to 0. Okay. So when questions ask you what's happening when the object hits the ground, what's its velocity when it hits the ground, what it's really asking is what's its velocity, or how long did it take just until the instant before it hits the ground, just right before. You can calculate stuff then. As soon as it touches the ground, we can't use the, you know, it's not in free fall. We can't use the constant acceleration equations anymore. Okay. All right. I'm going to do one example problem. So let's say that a ball is thrown straight up at a speed of 10 meters per second from a height of 3 meters. First, the first question is, what's the maximum height that the ball reaches? And second, what's the velocity of the ball when it hits the ground? Okay, so to use the constant acceleration equations, we have to specify those 4 values. So first, let's do the times first. So time equals 0 and time final. What we want to know is, what are the instants where we have information and where we want to find information? So what's going to be our time equals 0 instant? Yeah, right. Right at the instant that it's launched, because at that instant we know the velocity and we know the height. And what's going to be time final? For part B, it's going to be when it hits the ground. For part A, though, this is a case where we're going to have to choose different ones for the 2 different parts. It's going to be when it reaches the maximum height, because that's where we want to find information. Also, we know something at the maximum height. We know the velocity is equal to 0. For free fall problems, the positive direction, I'm just always going to use up. And so what do we want for our 0 position? On these, a lot of times it makes sense, not always, but a lot of times it makes sense to put the 0 position on the ground. So let's do that. Now let's list out what we know and what we want. Do we know the initial position? What is that? +3, yep. The ground is 0, and it's 3 meters from 0 in the positive direction, so it has to be plus 3. Do we know P final? Nope, that's what we're trying to find. Do we know V initial? We know it's 10 meters per second, the initial velocity. Well, we know the initial speed is 10 meters per second. Is the initial velocity plus 10 or minus 10? It's plus because it's moving in the positive direction. It's moving up. Do we know the final velocity? 0, yep. Remember, time final is when it reaches that maximum height. And we know that at that point, the velocity is equal to 0. Do we know the acceleration? We do in any free fall problem. So the acceleration is negative 9.81 meters per second squared. And then do we know time final? No, but we don't care about that either. We're not asked for it. So I think the equation that works with these is, I think it's the only one we've used so far, but, well, we used one other one once, but it's 6, the 2a times the quantity pf minus pi, that one. So we have 2 times p final is unknown, minus p initial. Oh, and I missed the acceleration. So 2 times negative 9.81 meters per second squared times pf minus 3 meters is equal to v final squared minus v initial squared. You have to multiply all of this through. The algebra is going to get a little messier on this than the stuff we've done so far. But you get negative 19.62 meters per second squared times PF plus 58.86 meters squared per second squared is equal to negative 100 meters squared per second squared. Any questions about what I did with that algebra? And so now I'm going to subtract 58.86, this one, from both sides. So you get negative 19.62 meters per second squared times PF is equal to negative 158.86 meters squared per second squared. And now the last step is I'm going to divide both sides by negative 19.62 meters per second squared. So PF is equal to so I have the negative 158 meters squared per second squared. I'm dividing the negative 19.62 meters per seconds times seconds. You get 1 meter to cancel, and you get all the seconds to cancel. And so you're left with units of meters, which is good. You know, we have position we're looking for, so we want it to be in meters. The negatives cancel, and you get a positive value of 8.10 meters. So the units make sense. Does it make sense that PF would be positive? Yeah, does it make sense it would be bigger than 3? Yeah, that makes sense. Those are like the kind of things you can think about with the answer. Like you don't really have any way of knowing um, if it should be 8.1 or 6.5 or whatever, but you can sort of get some clues to tell you things worked right. The units are right, the sign is right, it's bigger than 3, and that's right, you know. Any questions about that? And then for part B, we're trying to find the velocity the instant before it hits the ground. Is there any reason to change those specified values in this problem?
Do we need to change acceleration to being positive since we're going
Ooh, that's a really important question. We don't, and that's a really important question. And let me just finish this problem, and then I'll talk about that. But the acceleration is still negative 9.81. What's going to change is for part A, our time final was when it reached the highest point. Now our time final has to be when it hits the ground. Okay, everything else we can leave the same. So our time final now is the instant it reaches the ground. So let's list out what we know and what we want. A lot of this stuff still doesn't change, even though we changed time final. The stuff at time equals 0 doesn't change. So our P initial is still 3 meters. Our P final, do we know our P final? It's 0, yep. V initial is still positive 10 meters per second. Our V final is what we're trying to find. Our acceleration is still negative 9.81. And we don't know time final. The equation that works with this is equation 6. So we have 2 times negative 9.81 meters per second squared times P final minus P initial is equal to V final squared minus V initial squared. And so you get a value of 58.86 meters squared per second squared is equal to VF squared minus 100 meters squared per second squared. Did you already added the 100, I think so. Yeah, so you will get that once you add 100 to both sides. So 158.86 meters squared per second squared is equal to V final squared. Now take the square root, and you get V final is equal to, the square root of 158 is about 12.6 meters per second. We took the square root, so you need the plus minus. And now this one isn't quite as simple to choose the positive or negative of this answer, isn't quite as simple as it was with time. With time, it's just always positive. Velocity can be positive or negative. So which one do we want in this case? We have to think physically about what's happening in the problem. When it hits the ground, it's on the way down. So at that instant, it's negative. So the final velocity is negative 12.6 meters per second. Yep.
So on an exam, do you care where we start things? Like,
Nope. Yeah, that's fine. You could do the problem that way, and you'd get the same answer. Yep.
But you don't care.
No, I don't care. If I care, I'll specify, choose this one or that one. But so I wanted to say this, and I'm going to mention this again because it's a mistake that's so easy to make. People make it all the time. No matter what's happening, if an object is in free fall, whether it's going up or down or whatever, the acceleration is negative 9.81. And that seems confusing to people. The reason it's confusing is because I think you tend to tell yourself you have intuition about acceleration, but really your brain keeps trying to sneak back to thinking of acceleration as velocity. You have a good idea of what velocity is, but acceleration, you kind of just have to go with the math on it. But to make sense out of like what happens when you shoot something up into the air and it falls back down. So the most common thing that people do is they think, well, it's on the way up, the acceleration is positive 9.81. And when it's on the way down, the acceleration is negative 9.81. But think about what's happening when the object's going up, right? Its velocity is positive, okay? And you know that it's slowing down. From experience, you know it's slowing down until it gets to the highest point. So if it's slowing down, the velocity and acceleration have to have opposite signs, right? So that means that the acceleration is negative while it's going up. Once it gets to the highest point, it starts speeding up with a velocity negative. If it's speeding up, the velocity and acceleration have to have the same sign. So the acceleration has to be negative on the way down too. Okay. So I'll keep bringing that up, and unfortunately, like people are still going to keep making that mistake, but we'll try to reduce the number of times you make that mistake. Okay.